Well, the topic of my talk is wind engineering, the tallest buildings. And if I move on, as buildings get taller, I think it's fairly intuitive that wind becomes more and more important. So I've got this kind of exponential plot which illustrates this. And as you heard already this morning, that the number of tall buildings that is being built recently is exploded, if you like. This is from the CTBUH database showing the number of buildings over 200 meters tall in blue, and then over 300 meters in red, beginning back in the 1960s. So you could see this exponential growth. It's quite phenomenal. It's something the world hasn't seen before. So I put on the start of my career was kind of near the beginning of this, so I kind of got lucky as a wind engineer in that all these buildings need wind expertise. And RWDI was formed in 1986, although it had been around in a different, under a different name a few years earlier. So again, RWDI has been able to expand along with this tremendous growth in tall buildings. And we've been lucky enough to be involved in at least 13 out of the top 20 tallest buildings in one way or the other. Well, all the ones with red dots are ones that we've tested in our wind tunnels. I believe we also were involved on the Maury Tower as a kind of extra consultant, but we didn't do any testing. Well, going back to my own career, since I should talk about that, since this is a Lifetime Achievement Award. I hope my lifetime's not quite over yet. I've got a few more things to do. But this was one of the early tall buildings that I was involved with. It's the 72-story Bank of America Tower in Dallas. It was called something different. I think it was the Interfirst Plaza back in the early 1980s when we got involved. And I was kind of the new kid on the block back then as far as wind engineers were concerned. The big names were Alan Davenport and Jack Cermak. Fortunately, those two were far too busy to take this project on, so it was kind of a window of opportunity for me to get involved with RWDI. And so we worked with, HLM Design with the architects and the Mesra consultants, along with the local engineers, Brockett, Davis, Drake, were involved. So I had a wonderful opportunity to work with Bill Lemesra. And I remember on this building, because it's quite slender, we ran into vortex shedding, my first big building, and we had vortex shedding on it. So I remember calling Bill Lemesra and kind of spoiling his Christmas. It was just before Christmas, to present him with this building that, or this result where we saw vortex shedding fairly pronounced. Bill Lemesra took it very well, actually. He spent all of the Christmas holiday, I think, boning up on vortex shedding, and got back to me in the new year and said, "This is amazing." He was really enthusiastic about having learnt about this phenomenon. He said all structural engineers should know about vortex shedding, and it's very simple. It's all governed by the Strahl number. He understood it exactly. He loved the term vortex lock-in. It had a kind of dramatic tone to it. And so we worked on a solution which was, in the end, it was to stiffen the building, which got over the problem. And but we did look at putting in a damping system, and as some of you may know, Lemesra was one of the pioneers of using damping systems in buildings. Well, vortex shedding creates this peak in the response. So what we're seeing is the crosswind response, which could be building acceleration or the base moment on the vertical scale, and the wind velocity increasing as you go to the right on the bottom scale. And vortex shedding will produce this resonant peak at a certain wind speed. And if you don't have vortex shedding, you get the dotted line. It just increases uniformly rather than having the peak. So it depends where that peak lies on the velocity scale, which in turn depends on the frequency of the building, the natural frequency, its width, and its shape. So that's been a kind of a constant recurring phenomenon in my career that we have to deal with tall buildings. Again, going back to the mid-1980s, I got involved there with some buildings that were being developed. Well, one of them was Macklowe Properties. Harry Macklowe was involved on the Metropolitan Tower. And Eichner Properties was involved on the City Spire. So this was 57th and 56th Street in New York. And these buildings at that time, we thought they were very extreme because they had height to width ratio on the order of 10 to 1. And this was going beyond what had been done before. So we worked on both these buildings with the structural engineer, Rosenwasser Grossman. So we worked closely with Jacob Grossman, who sadly passed away a couple of years ago. And what we found was we were aiming, as these were residential buildings, to hit the 10-year return period acceleration peak of no more than 15 milli-G. Well, we found it couldn't be done without making the buildings horrendously expensive and impractical. But we could get down to about 18 or 19 milli-G thereabouts. And so the decision was made on those buildings to build in a space for a damping system, and but not put in a damper and see what happened. And both those buildings actually performed fine without a damper. We didn't have complaints. And so that 15 to 18 milli-G range became kind of our guideline, just based on experience. And since then, it's been used on many buildings, and has become kind of one of the 10 commandments of wind engineering. But I think we're now beginning to see that that criterion may have to be reviewed as we see buildings going even more slender, up to 20 to 1 and that kind of ratio, and having very long periods. So, but that has been the guideline for a number of years. And it's worked for us on many buildings. This is, each of those data points on this plot is a building. So we just numbered them from 1 through to 19 different buildings that were built in the 1980s and 90s. And you can see that most of them lie within the range of 15 to 19 milli-G. And they've all performed fine. There are 5 circle buildings, which where you could see there's some higher mauve points. Those buildings were what we predicted, or those are the accelerations that we predicted for the 10-year peak without any damping system. And it was decided that was too high, and so they were brought down to within the 15 to 18 milli-G range, down where those red triangles are, through use of dampers. And all these buildings have worked well. They haven't had any problems with them. So again, this is useful information because the motion criteria that we use are actually quite difficult to pin down purely on scientific and technical reasons. There's just too many variables, and there's nothing like having seen the actual performance of buildings and have we had any complaints. And if we haven't, then I guess the buildings performed well enough. In the late 80s, we were approached by Charlie Thornton of Thornton Tomasetti. He said he'd been talking with Chicago architect Harry Weiss about a half-mile high tower. And this was not a project for which there was a developer. It was just a kind of an exploratory look at what's involved if you want to go that high. We thought it was pretty extreme then, but now actually, there are buildings up at this kind of level, which is interesting. So we learned quite a lot on that. We saw vortex shedding again and looked at how to mitigate it by reshaping and using dampers. And then Thornton Tomasetti again and ourselves got together with, or joined Caesar Pelli architects for the Miglin-Beitler Tower in Chicago, which was a 2,000-foot tall building. And so the two men in your left-hand side of the slide are Lee Miglin and Paul Beitler. So there they are in our wind tunnel in Guelph, Ontario. So that project was again one that we learnt quite a lot. You could see it's got a very tapered form and stepping back as you go up in height, and that worked fairly well. So it would have been a workable building, but it became a victim of one of the periodic downturns that we see in the tall building industry, and so it was never built. But the team involved with that, Caesar Pelli, Thornton Tomasetti, and ourselves, RWDI as the wind engineer, did then become involved in the Petronas Towers, landing the job partly on the strength of what we'd learned on the Miglin-Beitler Tower. So these towers have this tapered form, and they are in a relatively mild wind climate, and they worked pretty well. There were some novel features, the Sky Bridge, which you can see at about the 45th floor, and that bridge was designed by Thornton Tomasetti so that it did not structurally link the two towers, so it had to sort of float at the ends, which involved having those struts below the bridge, which from a wind engineer's point of view introduced another interesting problem of vortex shedding vibrations off those four tubular legs. So there were some dampers put into those. So moving on now into the 1990s, this is the Taipei 101 building where we explored the effects of shape, and the eventual shape of the corners is shown in the bottom part of this slide. By stepping them back, it reduced the base moments by about 25%, which was a good thing because the initial foundations work had begun on the tower, and they had been based on code calculations, which were about 25% of what we measured they were about 25% lower than what we first measured. So this got the base moments down to a point where the foundations would work again. But the criteria being used for building motions on this tower, this shows some of the corner variations which you can explore in the wind tunnel, rounded corners and step back corners and so on. And to deal with the motion issues on this, we were trying to meet a criterion of no higher than 5 millig on a 6-month return period basis. And to do that required use of this damping system, which was designed by our motioneering group at RWDI. And we also took on the job, I guess, of being the prime on providing the damper, which was a bit of an experience for us as we had not done that kind of thing before. We decided after that experience that probably we're better to stick to consulting rather than trying to be a contractor. This shows the big damper, about a 600 metric ton mass, and it went through a typhoon in 2005, and I believe it was the daughter of the owner of this who took this video in the bottom right-hand side of the slide. And you could see the damper is moving at the building period of about 8 seconds, and doing exactly what we had predicted it would do. It kept the accelerations down even in this extreme typhoon to about less than 15 millig. Certainly, this was expected to exceed the 5 millig criterion, because that was only the 6-month return period, and we were looking at a much more rare event in this instance. But this kind of feedback information from monitoring a building is really valuable for people like ourselves, and this is another example of monitoring buildings, which is interesting to review the performance in terms of the sustainability or the greenness of the building, but also from a structural point of view as well. So having started to get into the field of dampers, RWDI has been involved with a number of projects. These show some, the Park Tower here in Chicago, the Random House building in New York, and the Wall Center in Vancouver. Examples of buildings where we've designed and installed the dampers. They all seem to be working pretty well. The one in Vancouver involved a liquid damper, a water damper, and so that was interesting, but it appears to be working fairly well. And here's some others: the Trump World Tower near the UN Plaza in New York and the Bloomberg Center. And this shows generally the reductions. On the right-hand side of the slide, you can see typically we were starting off without the supplementary damping system. That's what SDS stands for. It's about 24 to 28 millig, and we were getting down into the 15 to 16 to 17 millig range with the aid of the dampers. Well, more recently, we were involved with the Burj Khalifa, the world's tallest building, working closely with Skidmore, Owings Merrill on this. And we spent a lot of time in the wind tunnel working closely with SOM on the shape and the structural system, reorienting the tower even to get the wind loads down, the wind response down, and that was a fascinating project. And there's a quote from Bill Baker: "We virtually designed the tower in a wind tunnel." It was a privilege for us to be involved so closely with the design team. And I think that's been a theme of our involvement with tall buildings, is how closely it is necessary to work with the structural engineer and the architect in order to arrive at a good solution. So for shaping strategies, which are important to minimize vortex shedding, we often talk about softening the corners, tapering the building, varying the cross-sectional shape. All of those measures were implemented on Burj Khalifa, and even spoilers, which you don't see on the main tower, but the very final pinnacle at the top, which was a circular tube, has some fins on it to reduce vortex shedding off that top spire. The other option, which is shown at the bottom, is to basically create openings in the building and let the wind flow through, and that destroys the vortices. Sometimes with the wind tunnel tests, we have to look at scale effects. So I'm just showing this to illustrate how we sometimes have to build different scale models. So here's the top bit of the Burj Khalifa, modeled at 1 to 50 scale instead of 1 to 500, which would be the normal scale. And it allowed us to look at these scale effects. And we convinced ourselves that they were pretty negligible on this tower. On Burj Khalifa, we also looked at a novel tool, mesoscale modeling. This uses some of the same software used for forecasting weather to go back in time and look at some of the big historical events. So this shows a Shamal wind event over a period of several days occurring over the Arabian Gulf. You can see Dubai on the map there. And so here we were looking at wind speeds at the 500-meter level. And this kind of tool was really helpful in evaluating what's going on up at 500 meters, 1,000 meters. Most of the wind data is recorded down at 10 meters. We've been involved with the Chicago Spire, which you're probably familiar with. Unfortunately, that's another project that became a victim of financial issues. But the main thing from that experience was this tower had very long periods, like 17 seconds period for the first mode. So we had to start looking at not only the first sway mode, but also the second mode. So the higher harmonics need to be looked at. And this shows some of the work we've done on that tower in looking at the number of people on each floor who would notice the motion in red. And then if we look at the yellow bars, that's what would happen if we add in an active mass damper in this case. We didn't implement that, but we did do some interesting work in a motion simulator, which is shown here. This allows us to duplicate the waveform of motion that we actually predict from the wind tunnel tests, and to have people from the architect or the developer sit in there and actually experience them. Well, I see my time is up. There's a few more slides. Shanghai Center, the Nikhil Tower, aiming at something almost 1,500 meters high, and some of the issues of vortex shedding on that, and how it often occurs at a wind speed which is well below the ultimate wind speed, and this changes the way we have to look at the reliability of these towers. And here's Raphael Vinoli's tower that he spoke on last night. We did some work on the wind simulator in that as well, which I think he described. So there's still a lot more work to be done for tall buildings. They're designed using linear elastic methods. There's something to be gained by looking at what is the exact collapse mechanism as they are pushed even more. I think tall buildings actually could be useful as typhoon or hurricane shelters, if they could be designed right. This would get over some of the evacuation problems we run into in large cities, where the whole transportation system gets clogged up when people are evacuating. If they don't have to evacuate, that gets over that. And storm surge is inherently less effective in harming a tall building. But it does provide challenges on the building envelope. I think there's work to be done there in bringing the level of reliability of the building envelope up to the same level of reliability as the main structural system.